Okay, let's go ahead and get started. Welcome everyone to our GIA Knowledge Sessions. These are a series of talks and seminars about gemology that are fueled by our decades of research. And at GIA, we're so lucky to be able to study gems every day. And it's our mission to share our learnings and our discoveries with the world. So I'm excited to kick things off. I'm Kelly Giordano, a member of the content team here at GIA, and I'm joined by Dr. Evan Smith, GIA Research Scientist, and he's going to give us an inside look at what it takes to find and mine new diamond deposits. So before we get started, just a little bit of housekeeping. Everyone attending this is automatically on mute. So if you have a question, please submit it using the Q&A feature you'll see at the bottom of your screen. Feel free to ask questions as we go, and there will be a Q&A session at the end where Evan will have the opportunity to answer some of your questions. And we'll also be sending a recording of this either later today or early tomorrow morning. That message will also have a survey, and we would love to hear your feedback. So with that, I'm going to pass it over to Evan.
Thank you. Thanks everyone for joining us. So today, I'd like to talk a little bit about diamond exploration and diamond mining and what that sort of looks like. Now, my background is as a geologist. I spend a lot of time looking at diamonds and their inclusions and trying to understand what things look like in the mantle where diamonds form. But I've also visited some diamond mines and had a little bit of involvement with diamond exploration. So I have a little bit of knowledge about those things too. Now, I imagine most of you tuning in are familiar with this idea of the diamond supply chain. Diamonds come out of the ground somewhere and they go through a variety of steps, changing hands at each step and eventually ending up in diamond jewelry that people go on to enjoy. Now, most of you are probably more involved with the right side of this diagram, with the cutting and polishing or the manufacturing or the retailing or the grading that's involved within those steps as well. But today we're going to look at an area where you might not be quite as familiar, at the very beginning of the diamond supply chain, with exploration and mining. So diamond mining goes back many, many years, more than hundreds of years, even thousands of years. And diamond mining really began in India. So the first diamond mines were alluvial diamond mines in India. So they're digging sort of river gravels. That's an alluvial deposit. And that's been done for over 2,000 years. That's sort of when we think the diamond mining began. And for many centuries, this was the only known source of the world's diamonds. And it was the place that produced many of the world's most famous diamonds, like the Kohinoor diamond or the Hope diamond that's shown here. Much later in history, maybe around the 1500s or perhaps earlier, there's records showing that there was some smaller scale diamond mining in Borneo, the island of Borneo in Indonesia, in the province of Kalimantan. And that was another source of diamonds for a few hundred years. And then later, diamonds were found in Brazil. The first diamonds in Brazil were found in 1725. And people were there looking for gold. And the gold panners started recovering some of these beautiful crystals we can see over here on the bottom right. And they were there for the gold, and these beautiful crystals were sort of a byproduct, and they started using them as markers for card games until someone realized, hey, these are diamonds and we might as well be mining some of these too. So Brazil emerged then as sort of the new source of the world's diamonds, and eclipsed India and sort of overtook the global production for over 100 years. And all of these are sort of what I would call chance discoveries. Someone wasn't setting out to look for diamonds, they just sort of came across diamonds. But what if we had to replace all the diamonds in the marketplace right now? If we woke up tomorrow and there weren't any diamonds anywhere in the global marketplace, we had to go out and source new diamonds back at the beginning of the supply chain, well, we would start with diamond exploration. And we'd be looking at what kinds of different diamond deposits exist out in the world. Where do diamonds actually exist in nature that we might be able to access them. So in the last slide, I talked about some alluvial deposits, and that's an example of a secondary deposit. So here I just want to make a distinction between primary deposits and secondary deposits. So secondary deposits are examples where the diamonds have been eroded or washed out of some initial place they were and redeposited it, say in a river or along a beach. There are also marine environments where the diamonds have been washed out into the seabed or sort of worked on the shore. And there are also diamond deposits that were sediments that have sat and sort of lithified. They've turned into stone, and you have these examples of conglomerates, these sort of cemented together cobbles and pebbles that have diamonds embedded in them. These are all examples of secondary deposits where the diamonds have been eroded and transported, usually by water, and then redeposited into a new place. So those are secondary deposits. Primary deposits are places where diamonds have been brought to surface. And primary deposits are usually a volcanic, sort of magmatic type of thing. Usually we're talking about a kimberlite that has brought diamonds up to surface. And on the right here, you can see this is a diamond mine where they're mining a few different kimberlites, and they've got these open pits to extract the kimberlite ore. These are primary diamond deposits. Where do these diamonds in the deposits come from? I talked about this a few weeks ago, but diamonds form very deep in the earth. Most diamonds that we're recovering in mines formed about 150 to 200 kilometers down inside the earth. And there's no way we can dig down that deep. The world's deepest mines are only a couple kilometers at most. But the diamonds have actually been brought up to surface from 200 kilometers all the way up to surface by kimberlites and related volcanic eruptions that have transported this material up to surface. And because diamonds are so far removed from the place where they initially grew, it makes it really challenging to build an understanding of how diamonds form and where they really come from. A lot of the stuff that we know about diamonds comes from studying inclusions. And this is a sort of artist's picture of what a kimberlite might look like as it's erupting from 200 kilometers depth. Now these kimberlites, here they're shown as these red lines intersecting this slab of material up at the top. This is the continental lithosphere. So we've got the Earth's crust and this sort of keel, this thick cold layer beneath it. And this is what we sort of sit on in the oldest, thickest parts of continents. This is important when we're talking about primary diamond deposits, because most of the diamonds, when we're talking about diamonds forming at 150 to 200 kilometers depth, this is down below the graphite stability field where you're getting into the diamond stability field. So the most stable form of carbon here is as diamond. And this region right here in the sort of base of the oldest and thickest parts of continents is where most diamonds are thought to form. And then they're carried up to surface in kimberlites. And if you look around the world at where most diamond deposits are, both primary deposits and the secondary deposits associated with those, you'll see that most diamond deposits are sitting on or close to these oldest and thickest parts of continents. And on this world map here, those oldest, thickest parts of continents are shown in gray and this related beige color here. These are what we would call cratons, where the continent is very, very old, so billions of years old. And this association between diamond deposits and old, thick parts of continents is known as Clifford's rule. And it's now seen more as a guideline, Clifford's guideline, than a rule. But in general, the idea is that diamonds and diamond-bearing kimberlite eruptions are spatially associated with cratons. So on a first order, if you were looking for a diamond deposit, looking in and around cratons, these thick old parts of continents, is where we would expect to find diamond deposits and kimberlites that have brought diamonds up to surface. Now, as I said, a lot of what we know about diamonds comes from studying mineral inclusions. And here are a few examples of pretty common kinds of mineral inclusions trapped inside diamonds. And mineral inclusions in the diamonds, these are remnants of the diamond's birthplace. So as the diamond was growing, it enveloped some neighboring mineral grain, and that's now trapped inside the diamond. So this gives us an idea of what the place and the depth and the time looks like when diamonds have grown. These are little frozen snapshots. So we've got a couple different kinds of garnet here, and this green thing, this is a chrome-rich clinopyroxene. Here are a couple more kinds of mineral inclusions, a blue kyanite and an orange garnet. And here the host rock would have been something we called eclogite. And on the right, here's a little colorless inclusion. This is an inclusion of olivine. In this case, the host rock would be peridotite. And eclogite and peridotite, these are the two most common host rocks we talk about in terms of diamond formation at this depth of 150 to 200 kilometers. So diamonds are forming within these host rocks. And as we said, those mineral inclusions, those are pieces of the diamond host rock that have been trapped inside the diamond. So this is a little polished slab of one of these rocks that we would expect to find down at 200 kilometers depth. This is a kind of peridotite, and it's made up of green olivine and orthopyroxene. And then this purple material here, these are garnets, chrome-rich pyrope garnets. And if we imagine what diamond formation might look like in this environment, so if we've got fluid coming into this rock, remember we're down here at 200 kilometers depth, fluid penetrating into this rock and precipitating diamond crystals of carbon. So here we've got a diamond that's formed and enveloped a little piece of this rock. So now this diamond contains a little snapshot of this rock. That's a garnet inclusion. And if all of this material were broken up and swept up to surface, we would see both this diamond and its little garnet inclusion. We would also see lots of fragments of this host rock. And this would show up as these little garnet indicator minerals. So in the sort of diamond-bearing kimberlite at surface, we might find some diamonds with garnet inclusions, but we'll probably find more garnets that are loose and on their own that represent the host rock that's been disaggregated, busted up, and carried, swept up to surface in this volcanic eruption. So if we zoom back to sort of the continental thickness scale, here we've got the thickness of the continent and a diamond growing down here at maybe 150 to 200 kilometers. And as this diamond grows, maybe it envelops some mineral grain here. In the last slide, we talked about it being a garnet, but it could be anything. And then when a volcanic eruption sweeps this material up to surface, the idea is that you might have some diamonds, but you'll probably have many more indicator minerals, things that were in that diamond forming environment that accompany the diamond, and they're now present in probably greater abundance at surface. And these are what we call indicator minerals. So indicator minerals are mineral grains related to diamond formation. So they're there when the diamonds formed, and they're transported up to surface along with diamonds. And what we've found from looking at diamond deposits and searching for new diamond deposits is that there's this relationship where we find indicator minerals like these purple garnets or these green chrome-rich diopsides. Where we find these indicator minerals, we might find diamonds as well. And the benefit to looking for indicator minerals as opposed to just looking for diamonds is that the indicator minerals are more abundant than the diamonds themselves. If you wanted to explore for a new diamond deposit just looking for diamonds, you're going to have a much harder time than if you sort of broaden your horizon and look at all the different mineral grains that might have accompanied that diamond on its way to surface. So looking for indicator minerals, these sort of diamond friends, looking for indicator minerals is a real key to diamond exploration. This is a huge tool that's used all around the world. Now, if we talk about the kimberlite, this volcanic eruption that brings the diamond up to surface, what is it? It's a volcano, but it's not really like other volcanoes we're really familiar with, like you would see in Hawaii or like at Mount St. Helens. Kimberlite is different because it originates much deeper in the earth. So this is a mantle-derived magma, probably derived from deeper than 200 kilometers. And it's marked by this very, very high CO2 and H2O content. So it's loaded with volatiles. And that's the idea I'm trying to get across on the right here with this exploding pop bottle, this Diet Coke flying everywhere because it's full of CO2. Kimberlite magma is similar in that it has a lot of dissolved CO2 and water in it. And the eruption of this magma can be very rapid and energetic. That's how it's able to break up rock material and sweep it hundreds of kilometers all the way up to surface. And when we see this rock at surface, this kimberlite, in its simplest form, it's a very olivine rich rock. So I'm showing a little slice of kimberlite here, and the scale is very small. So these grains are about 1 millimeter across. And most of this light gray green material you can see is olivine. Kimberlites are usually packed full of two kinds of olivine, these sort of rounded lumps. These are olivine macrocrysts. This is sort of the mantle rocks that have been churned up and disaggregated into just rounded pieces. And then you've also got olivine phenocrysts that have a sort of flat-sided edges that look a little bit more like crystals. And the olivine in this case is thought to have crystallized from the kimberlite magma on its way up to surface. And in between these olivines, you've got all this grayish and blackish material. You've got a ground mass in there that's highly variable. Now, this is sort of the simplest form of kimberlite magma. We would call it hypabyssal because it hasn't erupted and come up above surface and disaggregated and lost a lot of its pieces and been mixed up and tumbled. What we see in reality is that kimberlites are extremely variable depending on what happens during that eruption process. If the kimberlite erupts up and then sort of resediments back down into the crater, or if it sort of pools in the crater, or if it sort of fountains up in making like a cinder cone, we end up with all kinds of different textures and mineralogies preserved inside the kimberlite. So it's a really complex rock type to wrap your head around. And an interesting thing is that when you look at one of these eruptions, one single kimberlite pipe can have multiple eruption episodes in it. It's not unusual to see 4, 5, 6 different discrete events of magma coming up to surface and sort of worming its way around previous eruptions and building up what we see as this final kimberlite pipe. And the other thing is, quite often when we find a kimberlite, we don't just find one, we find a cluster. Often a kimberlite will have maybe 10 or 100 even neighboring kimberlites over an area of, you know, many square kilometers, making up a cluster of kimberlites. Now, kimberlites were named after the town of Kimberley in South Africa. The first time we found kimberlites was in the late 1800s. So as we said before, we had diamond mining in India, later in Brazil, and then in 1866, the first diamond was found in South Africa. And shortly after that first diamond was found, people were looking around for more diamonds, and they found this volcanic rock hosting the diamonds themselves. So this is the first time we encountered a primary diamond deposit, actually hosted in that magma itself. And the rock type, this volcanic rock, was named kimberlite after the town of Kimberley, which was right there. And this was followed up by a whole bunch of exploration in the area. More kimberlites were found, more diamond deposits. This is the birthplace of the company De Beers, which was established in 1888. And over the course of maybe 100 years, there's been a lot of mining and a lot of research into what makes up a kimberlite and how we might find more deposits elsewhere. So I'd like to talk about some exploration elsewhere that took information we learned from studying South African kimberlites. So in the 1970s, this idea of indicator minerals had been known and developed to a more refined kind of approach, where especially garnets were not just recovered and studied by eye, but actually broken down in terms of their chemical composition. And looking at garnet composition was really helpful, because it's not just that you're looking for garnets that vector towards diamond deposits. You're looking for particular kinds of garnets. I showed those garnets that were purple in color. Those are chrome-rich pyrope. So if you're measuring the actual chemical composition and the chrome and calcium content of the garnets, you can plot up all sorts of garnets into different compositional fields and say that actually it's not just garnets, but it's these particular kinds of garnets, these chrome-rich pyropes usually, that we're looking for to vector towards diamond deposits. And that idea of sort of looking at indicator minerals in a more robust way is what led to the actual successful exploration of diamonds in Canada. So we're going to focus up here in Northwest Territories, where we've got these numbers 1, 2, 3, 4, 5. Numbers 2, 3, and 5. This is the Acadie mine, the Diavik mine, and Gacho Quay. These are big mines in Northwest Territories right now. And we're going to talk about how they were found. So we're going to zoom into this area with a satellite image here. So here we can now see Great Bear Lake, Great Slave Lake. This is sort of part of Northwest Territories here. The city of Yellowknife sits right here. And in 1978, so sort of at the time when indicator mineral geochemistry was being more refined, De Beers decided to look for diamonds. And they were looking here in this region. This is the Mackenzie Mountains. And in 1978, they had found some interesting looking indicator minerals, and they were hoping to find a diamond deposit in and around the Mackenzie Mountains. But what they didn't realize is that this is a region that's been glaciated. So glaciers have swept over this whole land. And these glaciers, they are almost like big, massive ice sheets that act like bulldozers. They move material and scrape all the soil away and sort of bring things right down to the bedrock level. So if you're looking at sort of loose sediments here in the Mackenzie Mountains, there's a good chance that they've actually been transported from the east to the west. And someone recognized this. There were two guys, Chuck Fipke and Stu Blusson, and they happened to be doing some mineral exploration work in the area and found out that De Beers was looking for diamonds. Now they knew that this region had been glaciated and that you were actually better off looking for those diamonds back farther to the east. So they took it upon themselves to undertake some diamond exploration. And starting in 1985, they picked up this indicator mineral train. They started finding especially these chrome-rich pyrope garnets and tracking them back in the direction of ice flow. So tracking them back where these glacial ice sheets are thought to have originated. And over the course of a few years, slowly but surely, they worked their way back, looking at this glacial till, the sediment that's been deposited by the glaciers, looking for these indicator minerals. And they traced this indicator mineral train all the way back to this little lake here. This is Lac de Gras. And they found that the number of indicator minerals they were finding went up and up and up. And then past this lake, they dropped right back down to nothing. So they knew that there must be something big going on around Lac de Gras. And in 1990, they actually found the first kimberlite, Point Lake kimberlite there. It turned out to be barren, so it didn't have any diamonds in it. But it quickly led to the discovery of other kimberlites in the area. And eventually, just a few years later, in 1998, this is what became Canada's first diamond mine, the Acadie diamond mine. So on the Acadie property, there are 156 kimberlites, but only 8 of them really are economic in terms of their diamond content. So you can see that, you know, just finding a kimberlite isn't enough. You need to find a kimberlite, and then you need to find the diamonds that are in it. So this whole search is almost like looking for a needle in a haystack, but worse. You have to find the haystack first, and there's a pretty good chance, more than 90%, that the haystack you found doesn't actually have any needles in it. So this is a difficult and kind of frustrating journey to find diamonds. But in the end, for Chuck Fipke and Stu Blusson, I think they really were met with great success after their perseverance. So exploration in Canada, as I mentioned, a large part of it was due to the success of glacial till sampling. So this is an example here. I just picked it because it's a nice map. So there's a kimberlite here called Ranch Lake Kimberlite, and the ice sheet in this region has swept over the area and spread sediments, almost bulldozed them from east to west. And these little dots you see here are places where someone has actually flown in with a helicopter and dug a sample of glacial till, dug up the sediment. And then that can be processed to separate all the tiny heavy minerals in it. And then someone will pick it by hand under a microscope and pick out these indicator minerals and then plot it up in a map like this. So this map is showing the concentration of these nice purple garnets, these chrome-rich pyrope garnets. And you can see they kind of make this bullseye pattern. There's a high concentration of them here, but they're really being swept all the way from this region here. And past that, you don't see any of these chrome-rich pyropes anymore. In addition to till sampling, people also use geophysical surveys. So let's say you found one kimberlite here and you expect there might be more in the area. It's very common to do a regional geophysical survey. So this would involve maybe flying over it with a helicopter or an airplane, or doing something on the ground. And the two main things that people are surveying for is variations in the magnetism. The Earth's magnetic field can be shifted in its intensity and direction slightly over top of that kimberlite pipe. The rock type changes the way the Earth's magnetic field behaves ever so slightly. The other thing it changes is gravity. So Earth's gravity is always pulling down and we feel it as constant, but there are actually minute variations from place to place. And if you have sensitive instruments, you can detect this variation in Earth's gravity, both in its intensity and direction. And you can detect regions where there are gravity highs and gravity lows that might be associated with rocks that are either denser or less dense than the surrounding rocks. So this also works well to pick out kimberlites because they're a different kind of rock that's been intruded into this surrounding country rock. You can also make use of lots of other tools. For instance, the vegetation sometimes is different over top of a kimberlite because the soil geochemistry is a little bit different, and even the water flow can be a little bit different. The groundwater can be affected by the presence of a kimberlite at depth. We can also look at topography. Quite often the kimberlite is a softer material because it weathers easily. And then if it's, say, swept over by a glacier, the glacier can kind of scoop out some of that material and leave a topographic depression. So quite often these lakes are depressions, and they're actually, these kimberlites are depressions that are lakes. So for instance, the mine Diavik, they actually had to build up a dam and pump water out because most of the kimberlites there were sort of topographic lows and they were sitting under a bit of a lake. So once you find a kimberlite, like we said with the needle in a haystack example, your journey's not over. There's a lot of work that goes into sort of characterizing the kimberlite itself and drilling the kimberlite to see how big it is, how it's shaped, how many different units might be in it, different kimberlite eruptive events. And you have to evaluate the diamond content of all those different units within a pipe. and eventually reach this decision: is this an economic pipe or not? Can you actually put in all the work to extract and process rock from this deposit and make enough money selling the diamonds to make it worth your while? Quite often the answer is no. So there's a lot of risk associated with making this decision. Now, when we're looking at the diamonds, quite often you do drilling to find out what the kimberlite looks like, and eventually you might take a bulk sample of a kimberlite to get a more representative idea of what the diamonds look like in a kimberlite before you were going to mine it. And here's a sort of just a random assortment of diamonds. These are from Diavik, and they've been sorted for their size, so they're all about the same size, but they haven't been sorted in terms of quality. So this is sort of a run-of-the-mill quality overview of some diamonds. And you can see there's quite a range in diamonds. My point here is that, if you had a diamond mine that's recovering a lot of really nice colorless octahedra like this, it's going to be worth a lot more money than if you have a diamond mine that's producing a lot of, polycrystalline material or gray things that don't make attractive high value gemstones. So this is a big part in deciding whether or not it's economic to mine or not. Not just the diamond grade, how many diamonds you're going to recover, but the quality of those diamonds and what the price is going to be. And if we look at diamond grade and price, this is a sort of arrangement of different diamond mines, or not mines, but kimberlites from around the world. And on the left side here, we have diamond grade in carats per ton. And on the right side, we've got corresponding deposits and their the value of the rough diamonds that come out of that deposit. So here's an example of a diamond deposit in the Democratic Republic of Congo, and it's a deposit that has lots and lots of diamonds in it, really high grade. So for every ton of rock that you mine, here it is right here, you're recovering 6 carats of diamonds. So compared to other deposits around the world, this is really high. But when you actually look at the diamonds that you're recovering from that deposit, the value is very low. A lot of them are not really great gem quality. And this affects the economics of that mine. So because you've got high grade and low value, they kind of balance out. And in the end, this does make an economic mine. And you also have deposits that are the reverse of this. So here's the Letseng mine in Lesotho. Now this mine has a very, very low grade. You almost can't see the bar here. It's well below 1 carat per ton. So there aren't that many diamonds in that deposit, but the diamonds that you do find are exceptionally high value. They're right up at the top of this chart here, reaching $800 per carat. And the reason for that is that the Letseng mine has a lot of diamonds like this one. So it has a lot of these extremely high quality type 2A diamonds in it. And unfortunately, these diamonds, they actually don't come from this regular population of lithospheric diamonds where we've got indicator minerals indicating those typical diamonds from 200 kilometers depth. These large diamonds, we've actually shown recently that they're super deep. So they're a little bit removed from the traditional indicator mineral model that we're used to looking at. So this just tells us that there's more to be thought of here. There are more tools yet to be uncovered in diamond exploration. If we're looking for different kinds of diamonds that maybe stray from our traditional models. So now, if we just look at the diamonds themselves from all over the world, we see there's a lot of overlap in the properties of diamonds from different geographic origin. And that makes sense because the diamonds themselves are just a mineral of one element. They're pure crystals of carbon. And when you look at the mineral inclusions inside them, like we saw towards the beginning, we have similar mineral inclusions from a lot of different deposits. So if I give you 3 different diamonds, you probably can't tell them apart in well enough detail to separate them in terms of geographic origin. There's just too much overlap. Now, this brings us into something new that GIA launched last year that's called the Diamond Origin Report. I just wanted to mention it here since we're talking about diamond deposits. So this is a report that confirms the country of origin for diamonds, which it sounds, how do you do that? I mean, based on the last slide I just showed, if all the diamonds look the same, how do you actually do that? And the answer is that, well, when the diamond is mined and pulled out of the ground, someone knows where that diamond came from. So the origin is known at the time of mining. So the way this works is that if you have a rough diamond that comes in for the GIA rough analysis service for polishing, then GIA can study that diamond and using very scientific methods can record all the features, sort of give a fingerprint of that diamond in terms of spectroscopy and other more advanced techniques. And now if that diamond goes back into the supply chain and gets polished, and even if it trades hands many times, eventually if we see that diamond again, the point of this service is that we can scientifically match the rough and the polished and allow us to transfer this known origin when it was mined, transfer that known origin to the polished good. So this is only for polished diamonds that have gone through this GIA rough analysis service. If you'd like to learn more about it, you can visit the GIA website and you can actually look up this sample report. And this is the diamond for it. It actually shows images of the diamond before and after polishing. This is the report number down here if you're interested. So now if we go back and talk about the mines themselves, a lot of people, when they're thinking about diamond mining, this is sort of the picture that comes to mind. People working with their hands, doing panning or sieving and collecting the diamonds by hand. This works really well. If you're really skilled with the pan, you can segregate the diamonds from, say, quartz or other minerals really well. And that's because they're different densities. So the diamond concentrates in this region of sort of darker grains here where you've got heavier minerals. Diamond is a little bit heavier. It's a more dense mineral compared to quartz or other more common grains that you would have here. So you can separate them by density really well by hand, or even on an industrial scale. Industrial separation of diamonds makes use of its density to sort of separate out what would be a concentrate and sort of eliminate some of this lighter material like quartz. Here's another example of a secondary diamond deposit. This is another alluvial deposit. This one's in South Africa. This is the Saxondrift mine. And here they're mining some alluvial terraces. It's a big scale kind of production. They've got heavy machinery and they're sort of digging up materials. You could call this like a strip mine where they're stripping this material from the surface and then they would be processing it to extract the diamonds. We've also got those primary deposits. So here are some examples of primary deposits where you're actually mining kimberlite, or in the case of Argyle mine over here, it's something that's very closely related to kimberlite, but it's a slightly different rock type. It's called lamprolite. And the Argyle mine is actually closing this year, so that's kind of sad. But it highlights the need for continued exploration so that we can find new diamond deposits into the future and uphold the current levels of diamonds within the global marketplace. There's always demand for new diamond mines to come online as old diamond mines get phased out and depleted. Here's an example of this open pit here on the right. This is the Diavik diamond mine. And as these pits have been dug down and the easily accessible kimberlite has been mined out, this mine has actually moved to underground mining. So now beneath these pits that you can see, there are tunnels sort of dug into the rock where they can mine the lower levels of the kimberlite underground. So some diamond mines make this transition from an open pit to an underground phase as mining proceeds. Here's a very large diamond mine. This is in Botswana. This is one of the top 10 largest diamond mines in the world. And the footprint at surface, these kimberlites, there are sort of two of them here. They take up more than 1 square kilometer. This pit right now is, I believe, about 260 meters deep, something like that. And you can see the wall rocks on the side, they're sort of reddish in color. This is country rock into which the kimberlites have been erupted. And the kimberlites themselves, there are two neighboring kimberlites here, and you can see they're digging this material that's a bit greenish looking. That's the kimberlite rock itself. Now I'll zoom into this area here so you can see what's happening at the bottom of this pit where they're mining the kimberlite. Here we've got some kimberlite material. It's been blasted and broken up. We've got a shovel, we've got a loader there, and it's loading up this broken up kimberlite into a haul truck that will bring this material up the ramp to a plant where those diamonds can be extracted. Over here, we've got a drill, and it's drilling down to make little tiny holes that will be packed with explosives, and they can fragment some more rock that will be then dug up in the next sort of sequence of events. Now, in any mine like this, they rely very heavily on their machinery, their infrastructure. Everyone likes to see these big trucks. These trucks are actually quite huge. There's a person here for scale. Now these trucks can haul, I think this one is about 170 tons. So it's a lot of material that can be loaded up here. And a lot of work goes into maintaining these trucks and all the other infrastructure on site, because it's very expensive if you have to shut anything down. One of the things that always has to be replaced on these trucks are the tires. So this is, again, at the Orapa mine, and this is the stockpile of tires they have. Each one of these tires costs on the order of tens of thousands of dollars. So it's really important that they manage this properly to have a successful retirement plan. Now, when we talk about all of this mining activity, what's underpinning everything is a really good mine plan. You really have to understand very well the spatial makeup of this deposit. We talked a little bit about grade evaluation and the diamond valuation. You have to know where within the mine you expect to find high value diamonds or low value diamonds, or rock material that doesn't contain diamonds that you might consider waste and put aside in another pile. Now, as we saw in the bottom of the Orapa pit, that solid rock requires some kind of explosives, and then it requires crushing. That's what we can see here on the right. So those haul trucks dump their material into this bin here, and there's a sort of a jackhammer on an arm getting ready to break up any large pieces that don't fall into what is behind here is a big pit with a grate on top of it. And below that is a big jaw crusher where things get crushed down to a specific size. So there's a lot of processing that goes into the ore. And it's surprising that some of the diamonds don't just get broken up into pieces. A lot of it is preserved. I mean, they want to be very gentle with this material wherever possible. So the processing of the ore involves crushing, sometimes washing to remove clay materials or fine stuff. The material needs to be sorted by size and density. And then the ultimate recovery of the diamonds could be by hand if it's a small mine, or it could be by grease table, which is a traditional method that's been used for hundreds of years. But now a very popular technique is Xray fluorescence. And this looks like this. So you've got some bin up here feeding material with diamonds and other non-diamond grains down onto a conveyor belt. This conveyor belt empties out into a falling stream of material that's illuminated by X-rays. Now the diamonds will light up, and there's a detector that says, oh, something lit up, that's a diamond there. And then it activates this air gun that can give a little puff of air and shoot this diamond off into a different bin, a bin that contains the concentrate of the diamonds, and everything else will fall down into this waste bin. X-rays are also used for a slightly different technique called X-ray transmission. But the idea is similar, where it's using X-rays to sort of identify what within this stream is a diamond and should be separated. Here's one more mine I want to show you. This is the Callaway Mine in Botswana. And on the top, you can see this big open pit, and a lot of this same working with drills and loaders and haul trucks coming out of this pit. And then here, what's interesting is that the processing plant is all exposed. So you can actually see a lot of what happens here. And I'm standing on top of the crusher. So you can't see the crusher because we're standing on it. That's what we showed in the previous slide with that big jackhammer on an arm. So that's here. So this crushed material is being fed down into all this system of conveyor belts here. In the distance, you can see a building, and this is where most of the diamonds are actually extracted. And then there are more conveyor belts bringing this material around. And most of the waste material is being put in this pile here. So this is sort of just giving you an idea of how complex this process is. They need to make all of this work like clockwork so that they end up making money on the diamonds rather than losing the money. So we've seen a lot of stuff here. We've talked about exploration. Now, if you're looking for diamonds, generally you're going to target one of these regions with old, cold, thick lithosphere. That's Clifford's rule, or better said as Clifford's guideline. And quite often people are looking for indicator minerals, either in a glacial till sample or in a soil or river sediments. And on top of that, a very useful tool is geophysical surveys, quite often by flying a helicopter over top of where you expect a kimberlite might be and looking for anomalies in the magnetic signature or the gravitational pull of the earth. And then when you actually do find a deposit that looks like it's economic to mine, we've got two different kinds of deposits here that have a slightly different approach. We've got secondary deposits. These are like the river deposits or beach deposits. And they can be anything from a small scale artisanal kind of operation to something that uses more heavy machinery with dredging or strip mining. And then these primary deposits, kimberlites, or like the lamproite at Argyle, these are quite often larger operations where they make an open pit, a cut into that material, and sometimes they do underground mining as well. And then all of this ends with this sort of elaborate scheme of ore processing to actually get those diamonds out of the host rock in a way that's cost effective. So there's a lot going on here that supplies this diamond supply chain. This front end where the diamonds come in is quite complex in detail. And if you ever get the chance to visit a diamond mine, I hope everyone does, because it's really interesting to see it with your own eyes, what goes on here and kind of the brute force behind extracting these little tiny, beautiful gemstones, and that they survive all of these things, the geological processes and the mining to be supplied into the marketplace. So that's all I wanted to say about exploration and mining. Now I think we have some time for questions.
We do. We have some time for questions. So thank you for everything that you presented in that presentation. We've got some really good questions. We've got a lot of really good questions. So I'm going to do my best to get through as many as I can. So we'll just jump right in. Are gem quality diamonds sparse because we're only able to dig so deep? And can we assume there are billions of carats of gem grade material that are out of reach and closer to the mantle?
Yeah, that's a good question. I think if we could dig much deeper in the earth, which I'm not saying we will be able to, but if we could, in theory, yeah, we could be able to access more and more diamonds. But inevitably, digging deeper always comes with a much, much greater cost. As you dig deeper into the earth, the rocks are under so much squeezing pressure from the weight of the rocks above them that once you get down, just a few kilometers down into the earth's crust, the rocks are under so much pressure that as soon as you dig a hole into them, the rocks almost explode back in on themselves. So it's extremely expensive to try to fight that pressure, and it only gets worse as you dig deeper and deeper. So it's really not realistic that we would ever be able to dig significantly deeper than we do right now and actually economically extract materials.
Okay. Do we see any active kimberlite eruptions today, quote unquote, or is it more historic as in they've all happened millions of years ago?
Yeah, the case is that they're essentially all historic. They've happened millions of years ago, and the volcanoes that we've witnessed within recorded history are different kinds of volcanic eruptions. None of them are kimberlites. So most of our ideas of what a kimberlite might look like when it's erupting come from studying the rock itself and recognizing that it would have had a lot of carbon dioxide and water in it, and it would have been a very low viscosity, kind of very energetic and explosive eruption. But those are sort of things that we've pieced together from the geological evidence as opposed to witnessing them firsthand.
So is there any particular reason why most of the kimberlites are in the center of the craton?
Well, the center of the craton, that's just where they go. I guess there isn't a great answer because we don't really understand exactly why kimberlites erupt where they do. We think that there's some relationship whereby there's kind of a chemical reaction almost between the kimberlite magma reaching the base of the continent and it exsolving some of its water and CO2 and transforming into more of an energetic eruption. And maybe if a kimberlite magma, a potential kimberlite magma, erupts somewhere else in the world and doesn't intersect those same kinds of rocks at that depth, it might not result in an energetic eruption and make its way to surface as a kimberlite eruption. But this is still an active area of research, why kimberlites erupt where they do.
So then is there a general zoning pattern where you find, like as you mine deeper, you're finding less or more diamonds or of higher or lower quality?
Yeah, I guess intuitively you might expect that if you dig deeper, you're getting closer to the diamond source and maybe you would be picking up better diamonds or more diamonds. But in reality, it doesn't work like that. The kimberlite has sort of ripped up all of this material and transported it more than 100 kilometers through all these tiny narrow cracks and mixed it all up before we ever see it. So once it reaches surface, the distribution of different kinds of diamonds or different populations of diamonds is really up to the eruptive style of the kimberlite. And the kimberlite can erupt in very different ways depending on what the rocks look like at the very surface. That last couple of kilometers of the eruption can make a big difference if you've got weak rocks like limestone that break apart easily. You can make a big eruption and that changes the distribution of the diamonds and the style of the kimberlite eruption, versus if the kimberlite is erupting into something really competent hard rock like granite, and then usually the kimberlite eruption is more constricted and narrow, and the textures that we see in the kimberlite are different. They reflect that difference in eruptive style. So what you actually find in any given kimberlite can be extremely variable.
Okay. How do we tell the difference between kimberlite and lamproite?
The difference between kimberlite and lamproite, they're easily confused. And I don't know that I have the best explanation to say what the difference is. They have a lot of the same textures in them. They can be differentiated based on their chemistry. You could divide them into two different groups. But yeah, in detail, what is it that makes, I think you would refer to the mineralogy on you know, in terms of what makes up the rock itself, and the potassium and sodium content and sort of geochemical measurements like that. But just to eye, they look the same. I think I would have to sort of revisit some of my petrology notes to give a really good answer what the specific difference is between kimberlite and lamproite. To me, they're very similar because they've erupted from the depth in the mantle, and they've sort of acted in a similar way to sweep materials up to surface.
So short answer is science.
Yeah.
How does X-ray fluorescence separation work if not all diamonds have fluorescence?
Yeah, so it's a different kind of fluorescence than UV fluorescence. So we talk about, you know, diamonds in the gem trade as having fluorescence. That's based on their illumination with ultraviolet. When you illuminate diamonds with X-rays, most diamonds do fluoresce. And there's this conveyor belt system with the air jet. Then when it detects fluorescence of a diamond, it sort of puffs the air and separates whatever it is that's lighting up. And that removes most diamonds. But it's true that some diamonds don't give a great fluorescence response and end up in the waste bin. And there are stories of diamonds all around the world, diamond mines all around the world, where they've ended up having some diamonds that make it through into the waste pile. So usually what's separated as this waste material is put off in its own pile of rocks. And at a later time, the company might come back and revisit that material with a slightly revised processing technique to try to extract those diamonds that were missed. Overall, it's sort of a balancing act between efficiency and actually getting all the diamonds, because you don't want to take too much time or else you're losing money.
Yeah, okay. Other than garnet and diopside that you mentioned, what are other primary indicator minerals?
Yeah, the main indicator minerals, so in terms of garnet, you've got the purple chrome-rich pyrope garnets that I spent most of my time talking about, but you've also got more red-colored garnets that are not part of that classic G10 category. And then you've also got more calcium-rich garnets that are more almandine pyrope, grossular kinds of garnets that are orange in color that tend to belong to the eclogitic suite. So there's a sort of purple, red, and orange garnets now. And then you've also got those green chrome-rich diopsides. Another indicator mineral is olivine itself. Olivine is very abundant, and specifically people look for olivine that's very high in magnesium. So forsteritic olivine is generally thought to be something that's derived from the Earth's mantle, as opposed to the olivines we might see at the Earth's crust. So olivine can also be an indicator mineral. And then you've got some opaque, sort of black minerals like ilmenite, picroilmenite, and then chrome spinel or magnesiochromite. Those are the main ones.
Okay. I think this will be our last one for time, but regarding garnet discoveries, why have there been no diamond discoveries in some areas that are really rich in garnets, like in the Czech Republic?
Oh, okay. Yeah. The Czech Republic is known for its garnets, but those are a different kind of garnet. So like I was saying with the recognition of these chrome-rich pyrope garnets, those are a particular kind of garnet that we think forms in very melt-depleted parts of the deeper mantle. But there are lots and lots of different kinds of garnets that form at shallower levels in the Earth's crust. So there are places, for instance, where they're mining garnets for sandpaper. They have lots of garnets, but they're not mantle-derived garnets. So because they're not mantle-derived garnets, they're not really considered the good garnets, the indicator mineral garnets that would tell you that diamonds might be traveling hand in hand with those garnets.
Okay, great. And I did see that we got a few questions about the Diamond Origin service. So as Evan mentioned, go to gia.edu to find more about Diamond Origin, and you can sign up. There's a form on the Diamond Origin landing page, which is gia.edu/diamond-origin. And you can ask us any questions about the service through that method. And thanks again for joining us. Thank you so much to Evan for giving us this fantastic presentation. If you have any other questions for us, please find us on Facebook, LinkedIn, Instagram, and Twitter. And thanks again for joining us. And don't forget to join us again next week, where we'll have Dr. Erin Palke to break down the analytical tools and techniques that we use in our GIA laboratories. So thanks again for joining us, and we'll see you next week.